Okay, this video is going to go over worksheet 9 and 10. It's important that you pause this and actually try the problem yourself. So I'm actually going to make these problems a little bit more challenging, make them more like AP physics sort of test. In other words, I'm going to tell you that the mass of this is equal to 80 grams. But I'm only going to tell you that the I, the rotational inertia, is 1/2 mr squared. And what I want to do is I want to figure out what the acceleration of this system is. So this is 1.2 kilograms, and this right here is 0.2 kilograms. So this is problem number 4 from worksheet 9. So the first thing I would like you to do is draw a force diagram for this object, and for the pulley. Okay, and then after you've done that, you can restart the video. So pause it, go ahead and make your force diagrams, and once you have them, then start it up again, start the video. So I'm going to assume that you have drawn your force diagrams. This is the force diagram for this object. This is the force diagram for this object, and I'm showing only some of the forces on the pulley. There would of course be a weight of the pulley, and there would be this push from this object here kind of pushing up that way. Both the weight of the object and that push force go right through the center, so they don't cause torques. So I'm not going to show those two. We're only going to concentrate on those. On the AP test, they don't need you to draw these to scale, but I want you to understand that this weight is much bigger than that weight, and it would be balanced by the normal force. And I also want you to understand that this tension here, which is smaller than the weight, is bigger than that tension. This tension on this object is the same as the tension on this object, same amount, and this tension is the same as that tension. Okay, so the next thing I'd like you to do is write a net force equation for this, a net force equation for this object, and then a net torque equation for this pulley. Okay, so go ahead and pause the video again. Okay, so the net force equation for this object would be the net force is equal to T2. So the net force is ma, so it'd be 1.2 times A. The net force for this object here would be the net force is equal to this weight minus that tension. And so that would be 2 minus the tension, and ma would be equal to that, so 0.2 times A. Then the net torque equation for this would be this tension times r, sine of theta would be 90, and then minus this tension times r, again sine of 90. And so I wrote it like this. I factored out the r. Of course, tension is also equal to I alpha. Then I can plug in what I is. It's 1/2 mr squared. Alpha is A over r. Then I can simplify. The r cancels a square. There's still one more r here and that r. They cancel. And so I'm left with 1/2 ma equals T1 minus T2. The mass of the pulley was 80 grams, so half of 80 grams is 40 grams, so that would be 0.04 A equals T1 minus T2. So here are my 3 equations and 3 unknowns. Notice I have a positive T2, negative T2. I have a negative T1, positive T1. So if I add all 3 of these equations together, the tensions will cancel. And so I have 1.2A plus 0.2A, that would be 1.4A, plus 0.04A, so I get it on the left-hand side, 1.44A equals, and then on the right-hand side, as I said, the tensions cancel, so the only thing I'm left with is 2. And so then I can solve it for A, and when I do that, 2 divided by 1.44, I get 1.38 meters per second squared. Once I know the acceleration, I can go back in and solve for T2. I can solve for this tension here. And I could also solve for T1 by plugging the acceleration in here and solve for T1. And those are some other questions that it's asking you for in number 4. Okay, so this is problem number 1 from worksheet 10. This is a real AP problem. Again, I'm going to tell you that the I for this is equal to 1.5 mr squared. Okay, so I for this object here is 1.5 mr squared. So now what I'd like you to do is I'd like you to draw a force diagram for this object, and for the pulley. Okay, so go ahead and pause the video. Okay, so your force diagram should look something like this. You don't have to have them drawn the scale on the AP test, but I do want to go over them real quick. That's going to accelerate upward, so this weight here, mg, is smaller than that tension 1. And this one here is accelerating downward, so 2mg, that's longer than this force here, tension 2. And this tension 2 is bigger than tension 1. That causes this pulley to spin this direction. So the next thing I'd like you to do is write a net force equation for both of these objects and a net torque equation for that object. And go ahead and pause the video. Okay, so the net force equation for this object would be MA equals tension 1 minus the weight mg, because it's accelerating upward. This one accelerates down, so therefore 2MA equals 2mg minus tension 2. Then the net torque equation for this one looks like this. It's going to be the torque T2 times R minus T1 times R, and I'm going to factor out the R. Again, net torque is equal to I alpha. I plugged in I as 1.5 mr squared, and alpha A over R. The R cancels the square, this R cancels this R, so I'm left with 1.5 MA equals T2 minus T1. Notice in these three equations, I have a positive T1 and negative T1, a negative T2, a positive T2. So I'm going to add all three equations together. And so I've got 1 MA, I have 2 MA, so that's 3 MA. And I have another 1.5, so that would be 4.5 MA equals, all the tensions cancel, so it's going to be 2mg minus mg, that would be mg, and so I can cancel the m, and so A would be equal to g over 4.5, and so we can actually figure out what the acceleration is. I can go ahead and plug in 10 if I wanted to, but I think I'm going to leave it just like that. We could also go back up here, plugging this in for the accelerations, and figure out the tension 1 and also the tension 2. And then finally, what I want to do is I want to find the normal force on this whole contraption here. Okay, so why don't you pause it for a second? Well, actually, why don't you go ahead and try to see if you can figure it out. Pause it, and after you find your answer, unpause it and come back and look. Okay, so try to find the normal force on here. I hope that you see that really I can kind of treat the pulley and that base as one whole system. And it feels the tension T1, T2. It also feels this weight of the pulley. It feels the weight of the base. And if I have to balance this out, I'd need to draw also another normal, and the normal would be equal to the sum of T1 plus T2 plus 7mg. Remember I said that you could plug in for A to figure out T1, plug in for A here and solve for T2. And so from this equation, plugging in those values, T1 is 1.2 repeating mg, T2 is 1.5 repeating mg, and then 3 plus 4 mg with 7 mg. Add that together, I get the normal is 9.7 mg, 9.7 repeating mg, which is kind of interesting because if somebody were to hold on to this and keep it from spinning, there's a total mass of 1, 3, altogether 6. There's altogether 10 mass altogether units. So that means 10 mg. So if you were just holding this, keeping this from spinning, the normal force would actually be larger than the 9.7 repeating. It would actually be 10 mg. But by the fact that this is accelerating upward and this accelerates downward, that decreases that normal force. Okay. Okay, this is number 2 from worksheet 10. So what I'd like you to do, since this is being released, this is going to start accelerating, this is going to start spinning, this is going to start spinning. I would like you to draw a force diagram for the car here, this pulley, and this larger drum here. So go ahead and draw force diagrams and pause the video until you get that done. Okay, so hopefully your force diagrams look like this. This T1 here is smaller than the weight that accelerates downward. On the pulley, T1 downward is the same as this T1, and that's bigger than this tension over here, T2, because it starts to rotate like this. That tension T2 is the same as the size of the tension over here on this big drum. So now what I'd like you to do is write a net force equation for the falling car and 2 net torque equations. Pause the video until you get that done. Okay, for the falling car, we know the mass, it tells us in the problem, so MA would be 895A equals the weight minus the tension. The weight would be 8,950 minus T1. The net torque equation for the pulley would be net torque is equal to T1 times R minus T2 times R, or I factored out the R. Also, net torque is equal to I alpha. They actually tell us what I is, so I plugged in 14. And alpha would be A over R. I divided both sides by the R to put it over in this side. That way I have T1 minus T2 and nothing else, just like I have a negative T1 there. They tell us the radius is 9 centimeters, so that would be 0.09 squared. Again, the reason why that is, it's A over R, but then I divided both sides by R to get rid of this R. So that's where it's 0.09 squared. And then for the last one, the drum, the net torque is equal to T2 times R, big R, this time it's different radius. And net torque is also equal to I alpha. They tell us what I is, 247. And alpha would be A over R. I divided both sides by big R, and so it's really going to be A over big R squared. They tell us what big R is, it's 0.52 meters. So now if you notice, I have a positive T2, negative T2. I have a positive T1, negative T1. So if I add all of these equations together, I'll cancel out the tensions. So why don't you go ahead and solve for A, pause the video until you get your answer. So adding these equations together, on the left-hand side, I got 3,536.9 A approximately. And the right-hand side, all the tensions cancel, and I'm left with 8,950. Solve for A, and I got 2.53 meters per second squared. That's not what it's asking, though. It wants to know the speed of the car when it hits. So they tell us the height is 4 meters, and it starts at rest. So you need to go ahead and figure out what the speed is when it travels at 4 meters at the very end. So again, pause the video and solve it, and then once you get the answer, then unpause it. So I hope you saw that's just simply kinematics. So I used Vf squared equals Vi squared plus 2AD. Vi is 0, the acceleration was 2.53, the distance it falls is 4, solve for Vf and you get 4.5 meters per second. For the next problem, number 3, the first part for part A, we're trying to figure out the force exerted on the axis here. So you need to draw a force diagram for this. There's a thread attached here, and there is a pin holding this axis here, and of course this has mass. So go ahead and pause the video until after you get the force diagram made. So there's 3 forces. There's a force right at the center, that's equal to mg. There's the tension force that's upward, and there's a force all the way at the other end. Since these are both equal distance from the center, They're both supporting half of the weight, so 1/2 mg, and I call that force F and this force tension. And then in the next section, what it says is that we're going to burn this string here, and so it's going to break, and we need to figure out the angular acceleration. And so you need to draw another force diagram for it where there is no tension anymore because the string's been burnt. Okay, so go ahead and draw that new force diagram right at the moment the string's burnt, so it really hasn't started rotating yet. It's getting ready to. So draw that force diagram, and then so pause it now, and then draw the force diagram, and then unpause it when you're done. Okay, so after that thread burns, right at the bare moment where it breaks free, it will start to rotate, but it's not translating. So we can actually jump down and answer part D. Once we know the force that this is going to exert, well, it has to be exactly equal to the weight because it's not translating to left, right, up, down, or anything like that. And so we know the answer to D. Okay, now we have to go ahead and find the angular acceleration, alpha. So there is a torque here, and you should be able to go ahead and calculate that torque and find alpha. And then you should be able to find the translational acceleration of the center of the rod here too. So why don't you go ahead and work on that and pause the video. So to find the angular acceleration, I wrote a net torque equation. That would be the weight times the lever arm length times the sine of 90. The lever arm length is L over 2. So it'd be mg L over 2. Net torque is also equal to I alpha. They tell us what I is. It's 1/3 ml squared. And then we can go ahead and solve this for alpha, and you get 3g over 2l. Okay. Now we want to find the translational acceleration of that center of mass. So why don't you go ahead and do that if you haven't done it already, and pause the video. Okay, so we can use the equation A equals R alpha. R to the center of mass would be L over 2, and alpha would be 3g over 2L. That's what we found earlier. Simplify, and we get 3/4 of g, and that's solving the problem. Okay, the last one here, number 4. We have this ball that is first, it's kind of sliding across the floor. There's no rotation yet. And then because of friction, it then starts to rotate. And so in this region here, it's both sliding and rotating. It's just beginning to rotate. And then here there's no more sliding, it's only rotating, as it rolls. Okay. So the first thing I'd like you to do is go ahead and draw a force diagram while it's transitioning from sliding to pure rolling. Okay, so pause the video as you do that. Okay, so this should be what your force diagram looks like. There's a normal force straight up, a weight force straight down. Those go right through the center, and so they don't cause a torque, and there should be a friction force which does cause a torque during the sliding phase. Okay, so now write a net force equation during this sliding phase, and pause the video. Okay, so this is what the equation should look like. It's just friction that changes the velocity of this thing. You probably plugged in what the coefficient was, 0.45, and the mass, which is 0.25, and g is 10, but I'm just going to leave it like this, like it's an AP problem. Okay. Now you're going to determine the linear velocity as a function of time during this sliding phase as this begins to rotate. So go ahead and do that and pause the video. Okay, so I used VF equals VI plus AT. So velocity is a function of time. VF is the initial velocity, which is 3, and this is actually slowing down, not speeding up, and the acceleration is given as ma equals this, and so that means a is mu k times g, and it's slowing down. And again, you could go ahead and plug in uk is 0.45 and g is 10, to simplify a little bit further, but I'm going to leave it like this, okay? Then the next part says find the net torque. Okay, so go ahead and find the net torque and pause the video. Okay, so the net torque is given as the coefficient of friction times m times g, that's the friction, times the lever arm, which is r sine of 90, so it drops out. You probably plugged in for mu k, m, g, and r, because they gave all those to you, but I'm going to write it like this. Okay, then it asks to solve for the angular velocity as a function of time, so go ahead and do that now then. Pause the video. Okay, so I'm going to use omega f equals omega I plus alpha t. And so the initial angular velocity is 0, so the angular velocity as a function of time would be 0 plus the angular acceleration is the net torque divided by the rotational inertia, so mgr divided by I times t. Let's say in this problem they told us what the rotational inertia was, and that's 2/5 mr squared. You actually have numbers that you could plug in, but I'm just going to make it more like an AP problem. And then I can simplify this, and I get 5 mu k times g over 2r. If you plug in the numbers here, you'll get the same number you should have got. So 5 times 0.45 times 10 divided by the quantity 2 times 0.02. And that should be the same number you have, okay? So that is the angular velocity as a function of time. Okay, then it wants to know, in F, determine the time at which the ball begins to roll without slipping. Okay, so realize we have this equation for translational velocity, that's true, and this is the equation for angular velocity, and that's true, during this slipping and sliding, or during the sliding and rotating phase where it's going from pure slipping to pure rotating. These both describe what's going on there. And so why don't you go ahead and figure out the time it takes before it starts to roll without slipping. Pause the video. Okay, so now we know V equals R omega. We can use that idea and plug in the equation for translational velocity. And we could plug in the equation for angular velocity. And then we could just simplify this. So the R's will cancel. I could combine the T terms, so I'm bringing this over. And so I got a common 7 mu k times g t. And again, you would probably plug in mu k and g. And then solving for t, I get 6 over 7 mu k g. And so that's my time. And then finally determine how far the ball travels while it's slipping and rolling. So go ahead and do that and pause the video. Okay, so then I use x equals VIT plus 1/2 AT squared to figure out the distance. So VI is 3, the time we found over here, so 6 over mu k g. And it's actually slowing down. Remember up here we found the net force, the magnitude of the net force I should say. And so that means the acceleration would be mu k times g, but it's slowing down, so I have a minus. And then again, here's the time that we found squared. And now the rest of it's algebra. And I end up with 108 over the quantity 49 mu k times g. If you plug in the 0.45 for mu k and the g is 10, I think you get a little less than half a meter.